A while ago I made this video about a homemade grid-tied inverter, which actually worked quite well. But below that video I got a couple of interesting comments that contain some information that I hadn't considered before, and that was so interesting in fact that it led me to build an improved version of this grid-tied inverter, and that is what today's video is all about. Now, this all started with this comment right here, which talks about something called load angle. Now, load angle is a concept from the world of synchronous generators, which are the type of generator that is used in power stations. So in a generator like this, which is connected to a power grid, you have a rotating magnetic field that rotates at a constant speed, which is proportional to the frequency of the power grid that the generator is hooked up to. Also in there is a rotor that goes round and round at the exact same speed as the magnetic field, hence why it's called a synchronous generator. But there is a difference in angle, or a difference in position rotationally between that rotor and that magnetic field, and that difference is called the load angle. And the reason for this is because the rotor is being driven by something, right? Because that rotor is connected to the shaft of the generator, which is connected to some kind of power source, like, let's say, an engine or a steam turbine or a hydro turbine, you know, a prime mover, something that drives this power generator. And so the way you can sort of imagine this is as if the rotor is trying to pull along the magnetic field, and because of this the rotor is slightly ahead of the magnetic field. You can also have a I wanted to say reverse, but negative load angle, right? So with a negative load angle, the rotor is slightly behind the magnetic field, so then it's the other way around. The magnetic field is dragging along the rotor, in which case the machine is operating as a motor. So now the rotor is not being driven by something, but the rotor is driving an external load. So that's, you know, a synchronous electric motor. So I'd like to go over to the computer right now, where I have a little simulation set up to see what this means from an electrical perspective. Okay, so this right here is the equivalent circuit of a synchronous generator that is connected to a power grid. So the voltage source over here represents the power grid itself, and these components over here represent the generator. So this is the EMF, or the induced voltage of the generator. This is the resistance of the coils or the windings of the generator, and this is the inductance of the windings of our generator. And then, you know, the output of the generator is somewhere over here, right? So the output terminals of the generator, they would be, you know, somewhere between the grid and this. Now, when I run this simulation, you will see that pretty much nothing happens. So you can see that we have an AC voltage on our grid, but there is no electric current, there is no power. And the reason for this is because at this point, the EMF of our generator is exactly the same as the voltage on our grid. So there is no difference between them, therefore there is no electric current. But now, watch what happens when I start changing the phase of the EMF of the generator, which I can do with my phase slider over here. So I'm just going to shift the phase a bit. There we go. And immediately, if you look at our power chart, you can see that we start producing power. So we're feeding power into the grid. Now, it looks a little bit weird, so I'm just going to fast forward the simulation and give it some time to sort of equalize out. There we go. So you can see that we are now producing power, right? The generator is now generating, if you will. And you can also tell that by looking at the voltage and the current on the power grid side, because you've got the original voltage, which is still the same, but then you've got this electric current that goes in the opposite direction, right? So you're pushing electric current back into the grid. So effectively, that means you're feeding power into the grid. Now, this phase shift that I've just introduced, that is the electrical equivalent of the load angle that we just talked about. So what I've actually done here is I've changed the load angle of the generator. And by having a positive load angle, we're producing power. But what about changing the voltage instead? What if I don't change the phase of this? So just going to set it back to 0. There we go, 0 degrees. What if I don't change the phase and instead change the amplitude or the voltage of this guy? So we're just going to increase the voltage, and once again just fast forward the simulation a bit. There you go. So now you can see that we're also producing power, but we're also producing negative power. So, you know, we have positive power, positive, there we go. Now it goes back down to negative. So the net result is that we're not producing any power at all. And this is known, of course, in the electrical engineering world as reactive power, right? There is no real power being generated or consumed. It's just energy being shoved back and forth. That's what's happening here. So what does all this have to do with that grid-tied inverter that I built? Well, as you might remember from that video, I used an H-bridge to generate the AC, and then I used a passive filter consisting of an inductor and a capacitor to sort of filter that choppy PWM signal from the H-bridge into a nice clean sine wave, and then I connected the output of that to the grid, or at least to the low voltage side of a grid connected transformer, but let's not worry about that too much. So does that look familiar to you? Well, probably it does, right? Because it's awfully similar to the equivalent circuit that we just looked at, except maybe for the capacitor, but it turns out that doesn't play a huge role in this story. And so what this means is that in order for an inverter with this design to work, you would expect there to be a phase shift between the output of the H-bridge and the AC voltage on the grid. But that wasn't the case in my inverter design, because when I built this inverter, I simply thought, you know, the output of the inverter needs to be synchronized to the grid, so the H-bridge also needs to be in phase with the grid, not taking into account that there is this filter sitting in between the H-bridge and the actual output of the inverter. And so basically this is what this comment was trying to point out, you know, how can this inverter work if you're not using any phase shift on that H-bridge? And of course I was using the voltage, the amplitude of the H-bridge to control the power output, but as we've just seen in the simulation, changing the voltage shouldn't really do anything, or at least it shouldn't generate real power. So I was wrong. That there is one thing that doesn't explain, which is why did the inverter actually work? I mean, I didn't fake those results. The equipment that I used turned out to be accurate because I verified that in a bunch of ways. So if all of this is true, then why did the inverter actually work in that video? Well, let's take a look at another simulation to find out. Now, this simulation is very similar to the one we looked at earlier on, except this time I've actually used the components and the component values that were used in the grid-tied inverter. So as you can see, we've got the 100 microhenry filter inductance, the 35 microfarad capacitance, and the 50 milliohm resistance connected in series with the output. And that is actually the shunt resistors that I put on there that I used to be able to probe the electric current with the scope. And as we are about to see, that actually makes a surprising difference, but we'll get to that. So let's start by taking a look at what happens when I run this simulation. So I'm just going to click Run. And at first, again, not much is happening. So you can see that there is some current flowing and there is a little bit of power, but I'm not sure if you can see the numbers on camera, but it's only 1 watt of power. So basically, again, nothing happens, just like before. So now let's see what happens if I start changing the amplitude or the voltage of the H-bridge over here. So I'm just going to slide this over. And this time you can see that we start producing a significant amount of real power. You can see we're producing about 80 watts of power on average. So unlike with that previous simulation where, you know, increasing the voltage only caused reactive power, we're now actually producing a very large amount of real power. Now, you can get very mathematical about this, but basically the reason why this happens has to do with the amount of inductance versus the amount of resistance that is present. So in this case, the inductance that we're using is a lot smaller than in the simulation we looked at before, and the resistance is a lot bigger because we have that 50 milliohm shunt resistor connected with it in series. You can see that the power factor is not perfect, right? The current and voltage are not exactly opposite, and there is still some small amount of negative power. And by changing the phase, I can optimize that, or I can sort of eliminate that problem. So if I just change the phase a bit, like this, also increase the speed, and then lower the voltage. Just doing a little bit of trial and error here. So this is quite tricky to do with these little sliders. Perhaps I should have used a different scale on them. But you can see that after a little bit of tweaking, again, we still have about 80 watts of power, but now these two are they're pretty much 180 degrees apart, as you can see. And also we've eliminated that negative power. So by changing the phase along with the voltage and using a sort of a combination of the two, you can get to a more optimal power factor than you can by only changing the voltage. Right, so what all of this tells us is that in order to get the best possible performance, we're going to need both an increase in voltage and a shift in phase, and sort of find an optimal combination between the two to get the best result. Now, I figured that the best way of achieving this would be to have individual control over both the voltage and the phase on the actual inverter, just like I do in the simulation with my little sliders. What if I could also do that on the inverter itself? That way I could simply, basically through a bit of trial and error, I could make small adjustments to both the voltage and the phase and sort of get the optimal power factor for every amount of power that I might want to output with this device. So in order to do this, I needed to add an additional knob or an additional potentiometer to the inverter, which is what I did. So I added an extra potentiometer, which I connected to the microcontroller that drives the H-bridge, and then I needed to change the software a bit so that it can actually, do this phase shift. I implemented the phase shifting in the software in sort of a crude and really simple way. So basically, as you may remember from that previous episode, we're using a lookup table to generate that period of a sine wave, or rather half a period of a sine wave. So basically a list of numbers that corresponds to 1/2 of a sine wave, right? So instead of starting at the first number in the list, you start at, let's say, the third number or the 10th number in the list. So by starting at a later point, that effectively shifts the whole thing to the left. That's how it's done, okay? So this potentiometer, when you turn it, the further you turn the potentiometer, the higher the starting index in that lookup table becomes. So now let's go over to the inverter and see if this actually works. This is the improved version of the grid-tied inverter. And as you might be able to see, we've actually changed a whole bunch of things about it. So first of all, I've made this nice little sort of control panel thing, which has a current gauge to monitor the input current, and of course the two potentiometers for changing the voltage and the phase. I've also added, or rather moved this cooling fan much closer to the heatsink of the H-bridge to provide better cooling. And I've changed the shunt resistor from 50 to 25 milliohms by adding a few extra resistors in parallel with it. For this test, we're going to be powering it from this 24 volt LiPo battery pack over here, and we're going to plug it into this extension cord which is hooked up to the grid. As you can see, it's now at 229 volts AC. So we're going to plug the output of the inverter right into this. I'm just going to set this to power. There you go. And also, this time for the test, I've actually wired up the scope to the output, or rather to the low voltage side, of the inverter. So we are monitoring both the voltage and the electric current using that shunt resistor. Right, so we're just going to plug this in here. And so now immediately on the screen of the scope you can see the AC voltage of the power grid. So that's very nice, but there is no electric current just yet because the inverter is not turned on at this moment. So in order to do that, we're going to press the yellow button, which will reset the microcontroller, and then hopefully the inverter should start working. There you go. So it had a little bit of trouble there synchronizing. It just does that sometimes. Kind of has to do with the combination of voltage and phase you pick in the beginning, it seems. But as you can see, we've now got an electric current flowing, and you can also see on the power meter that we're producing about 30 watts of power right there. And the power factor is about 58, 57. So that's not too great, is it? So let's just turn up the voltage a little bit first. There we go, so we're at 60 watts or so. And then we're going to shift the phase. Just give it some bit more voltage, bit of an extra phase shift, 99 watts. So we're about 99, 100 watts of power, and the power factor is 92, which is pretty good. This sort of being able to tweak the current and the phase and the voltage is really nice, and we're getting a pretty good power factor, but we already got a pretty good power factor last time too. But what I think is important to realize here is that if you look at the current waveform on the scope, you can see that it's pretty distorted, right? So let's just turn the voltage waveform off for a second. You can see that's our electric current. Now, I don't think that is very pretty. I mean, it's not terrible, but it's also not nice. You know, it's pretty distorted. So I want to fix this. And actually, there is another YouTube comment below that video that contained, quite possibly, a rather good hint of how we can deal with this distortion. More specifically, I'm talking about this particular comment, which says that the cause for the distortion in our current waveform might actually be the distortion of the voltage on the power grid itself. Let's take a look at the voltage waveform just before I plugged in, or well, just before I turned on the inverter. So this right here. Now look at this waveform very closely. It's not actually a very nice clean sine wave, right? You can see how the peaks or the tops of these half waves are sort of flattened off a little bit. Now, the reason this happens is because of full bridge rectifiers. Because a lot of devices these days have bridge rectifiers with diodes on their input to convert AC into DC. And what those do is they draw a big peak of electric current right at the top of each half wave of that sine wave. And so when you have millions of devices all across the power grid that all draw these sharp peaks of electric current right at that moment, that sort of starts, flattening off those peaks. So here we have yet another version of the same simulation actually that we just looked at. So we've still got our power grid over here and our inverter on this side. However, this time I've also connected something else to the power grid, which is this over here. So this is, as you might recognize, a full bridge rectifier made of diodes, followed by a capacitor and a bit of load resistance over there. So this represents a power supply, or perhaps a lot of power supplies with bridge rectifiers on the input being connected to the grid. And so what this is going to do is hopefully give us that same sort of distorted waveform on the power grid, so that we can see what happens to the current from our inverter when this is the case. So if I'm just gonna open this switch first to disconnect the inverter from the grid and run this. Maybe not at full speed. There we go. And so if you look at the grid waveform over here, just kind of zoom in on it, you can see that it kind of has those same flattened peaks that we saw on the scope during our test. So this is maybe not 100% accurate, but it's kind of similar to what we saw on the scope. So let's see now, if we close this switch, what the current from our inverter is going to be like. So I've just chosen some random voltage and phase combination here. But you can see that our current is no longer a nice pure sine wave, but now it's sort of this, well, I guess a spiky mess. And it changes in shape depending on how much phase shift and voltage you use. You can see if I change it there, it kind of becomes a bit different, or if I use a higher voltage, again, you can see it changing. So it changes depending on how much phase and voltage shift there is. But you can see that it kind of looks very similar to the distorted current waveform that we saw on the scope during the test. So now the question is, how do we fix this? Well, I have a pretty simple idea about this. What if we just take that lookup table that the inverter is using to generate the sine wave, and we just chop off the top of that sine wave. We just make it produce a sine wave that is more similar to the one of the power grid. That should reduce the distortion in the current output. Now, I've uploaded a new version of the software in which the top of the sine wave sort of is chopped off. So let's see if that helps in reducing the distortion in that current waveform a bit. So we're just going to plug this in. There you go. And then we're going to try to turn it on. Okay, so right now it does still look like there is quite a bit of distortion, but we are still at pretty low power, about 30 watts. So let me just shift the phase a bit first. Okay, let me give it a bit more amplitude. Alright, so we're at 97 watts, and the power factor is now about 95, so it's actually a bit better than it was before, and you can actually see that it looks quite clean on there as well. I mean, there is still some distortion, but it is actually better. Actually, I want to see if we can get some more power out of this too, so we're just going to crank up the voltage. There we are, 136 watts. The power factor was actually 98 for a second there. That is incredibly good. That actually looks really quite good. So we've got the grid's voltage is this one over here, and then you've got your current waveform, which is pretty much exactly lined up perfectly, 180 degrees apart from it. The distortion is also pretty low now. I mean, it's not perfect, but it's a lot better than it used to be. I'm actually really quite pleased with that. I mean, surely it's probably nowhere near a professional grade grid-tied inverter, but for a thing that's built using an Arduino of all things, I'd say that's actually pretty good. So there you go, right? The grid-tied inverter is a lot better now, and it is thanks to the people in the comments section. So if you ever have thoughts about videos that I make in general, so whether it's suggestions, tips, questions, ideas, whatever it is, yes, feel free to post it, because it might actually turn out to be incredibly useful, even if you don't necessarily expect it to be. Anyway, I hope you've enjoyed this video. Maybe if you really did, then consider subscribing to this channel, of course. And all that's left for me is, of course, to say thank you for watching.